fabric of space and time. We will try.
Would that be quantum physics?
Yeah, that's when you get into the funky stuff that you get theorists making up stuff that they're either hailed as genius or forgotten, one or the other. A friend in graduate school who'd been working on his doctoral dissertation, and he switched and he said, what I wasn't told before I started was there was a 0.5% chance that it would be brilliant and Nobel Prize worthy. 99.5% that it was just pure crap. It was the pure. All right, next layer down. The next term, acceleration. And the symbol that they use for that we use for acceleration here is A, with a vector symbol over it. And as with, there's average and instantaneous. And instantaneous is the default. We'll deal with a lot of problems where acceleration is constant, in which case instantaneous and average are the same. Let's see, get myself some space over here. Now, acceleration can be looked at the time rate of change of velocity. Or the acceleration is change in velocity over change in time. And technically that's the average velocity, the average acceleration, so that would be A. Now, because there's not really a bunch of confusing stuff in physics already, they decided that there is a scalar term that's sort of an analog of that, and that is called acceleration. The symbol, that without the vector symbol, so it's just A. Now, part of the problem, they got 3 physics courses going on right now, and they all start roughly in the same spot. And so I get to the certain point where I'm thinking, all right, can I say it to this group or can I say it to the other group? So I apologize if I'm repeating some stuff I've already said. It's because I think I've said it to the other group and not this group. So with that, so on a quiz or test, how do you know which acceleration is wanted, or in a textbook? From context. Now, that doesn't really help if you're just starting out trying to learn context. Usually, in a textbook, they're looking for vector acceleration when they ask for acceleration. Not always, but usually. Probably the 90% rule. On quizzes and tests, if in doubt, ask. But usually, I think I've gotten to the point where I'm pretty consistent on it, is that if I'm asking you to find acceleration, I will put one of those 2 symbols, either A with the vector symbol or A without, just to let you know which one I'm talking about. Now, the direction of acceleration is the same direction as the change in velocity. I got a formula right here. I got a vector symbol. I got only 2 vectors. I got change in velocity. I have acceleration. They have to be the same direction. But it's not always easy to think of it that way. If I am starting here, my velocity is, all right, it was sort of doing it in rounds, but how about in unison? Let's just warm my heart. There we go. 3, 2, 1, 0. That's so much nonsense. Almost a course of English. Don't worry, you'll get another chance. All right, so I'm starting here, and then I start moving in the negative direction. When I go from 0 to moving in the negative direction, is that a positive change or a negative change in velocity? Riley, it looks like you want to say it. But you don't look confident. Anyone want to back her up or just do the Riley, how could you? How do you find change anyway? Besides the quick calculations. If I go from 0 to -3, 0 meters per second to -3 meters per second, and I want to find so those are my velocities. How do you find change? This is one of the few always in physics. A lot of times there's hey, this works for this course, but this is one of those things that is always true. Change is always final minus initial. So this would be V final minus V initial. Change in position, final position minus initial position. Change in your pocket, it's how much money you had at the end of the day minus how much you started with. My final velocity is -3, my initial is 0, so if I do -3 minus 0, I think somebody said it, but the door was opening at that moment. I hear you, 3?
Yeah.
Or -3?
3.
It'd be negative.
So we have a disagreement here. We can settle like physicists with knives, or
-3.
you feeling confident?
You're not.
And you're backing up the negative? It's -3. You subtract 0 from anything, you end up with what you started with. If in doubt, use a calculator. But -3 minus 0 is -3. This is a negative change. My change in velocity is -3 meters per second. So my acceleration is negative. So I started here, I start moving in a negative direction, so I go from at rest to moving in a negative direction. That is negative acceleration. If I started here and moving in the positive direction, what was my acceleration? Suppose I'm moving in the positive direction and I slow down.
Still positive.
Why is it still positive?
It's negative because you're slowing down, losing speed.
All right. We can do it from a number point of view because who doesn't love numbers? Let's just do this. If I'm going +3 meters per second and I slow down to 1 meter per second, what is my change?
Your change is negative.
-2 meters per second. Well, you can always find it by taking the final minus the initial. So if I'm going in the positive direction and I slow down, it's a negative acceleration. If I'm going in the negative direction and I speed up,
It's positive.
It's still negative.
negative. Because my velocity is becoming a greater negative number. So what we end up with here is if velocity and acceleration are in the same direction, I'm going to speed up. So if acceleration and velocity are both negative, I speed up. If they're both positive, I speed up. So speed up, velocity, and acceleration, same sign. If I slow down, so they're sort of going against each other, velocity and acceleration, opposite signs. There are a number of students who get into this rut of negative acceleration means slowing down, positive acceleration means speeding up. The sooner you can break yourself of that, the better off. Negative acceleration, we're talking about vectors here. Negative acceleration, I need more information to know if that's speeding up or slowing down. So, let's assume up is positive. What is the velocity of this marker right now? Intended to be, yes, my hand does shake a little bit. When I let go, velocity positive or negative as it falls? What was the,
You kinda sped up when you drive.
I said up was positive, velocity cares about the direction it's moving in. The velocity is negative. What was the acceleration? Did it speed up?
Yeah.
It sped up, acceleration, velocity, same direction. So the acceleration would be negative. As I said, up was positive, acceleration is negative. Let's look at this in a slightly different way, since we have done forces first, which is a disadvantage of the other groups. Newton's second law, what I consider the most important equation in physics. I got only two vectors, vector quantities in this equation. Again, incredibly important equation. The force, this is the total force is equal to mass times the total acceleration. It looks a whole lot like W equals mg. Matter of fact, if I take an object and I just let go, then it's falling. Ignore air resistance. What are the forces acting on an object that's falling? I'm going to nitpick at this point. What's the name of the force? Yeah, you're the one who said gravity.
Oh yeah, gravity.
What's the name of the force?
Oh,
Thank you, Reed.
Wait.
Yes,
Yeah, weight.
weight. So I have weight acting down. And so plugging into that formula, I have weight is equal to mass times, well, the acceleration due to gravity, which we symbolize by the letter G. So this weight formula comes from this. All right, so I've got two formulas here. The total force and the acceleration are in the same direction. So if I'm moving in the negative direction, my velocity is negative, and someone pushes me from behind in the direction I'm moving, will I speed up or slow down? The force is in the negative direction. My acceleration would be in the negative direction. My velocity is in the negative direction. Velocity and acceleration, same sign, or same direction, I'm speeding up. If I move it in the negative direction and someone pushes me that way, so pushes on me, stops me, what's the direction of the force? And somebody, I think, said it. Yep. What's the direction of the acceleration then? Just repeat what the other person said. Yeah, it's positive. Again, force and total force and acceleration, same sign. So if the force is in the direction of movement, you'll speed up. If the force opposes the motion, you'll slow down. That goes hand in hand with that. Think of acceleration and the total force being the same direction. Did I do the three accelerators in a car? That's another. All right, we will end on, if you're driving, assume automatic transmission. What are the three accelerators you have access to as a driver?
the gas
There's one.
Brake.
That's two.
and then clutch. Oh.
The gear.
I assume, ignore the gear. I said automatic transmission, so hopefully you're not shifting.
The person?
Oh,
Sorry?
The person?
No,
where is
not the engine.
The car?
You have access, I guess you do have access to the car itself. I'm talking about the things that, the devices that you have access to.
Oh, emergency brake.
I'm not gonna throw that in with the brake.
Speed
Little
up.
thing that tells you how fast you're
The
going.
speed.
Not the speedometer. Reed, what did you say?
Do better.
You wanted the speedometer? Or you were just saying,
No way.
remember, we're talking about vector acceleration. It's the change in,
The wheels? Yeah.
The steering wheel.
The wheels.
which wheel?
Tires.
Not the tires.
Steering wheel.
Steering wheel. Steering wheel is an accelerator because it helps you change direction. You turn the wheel, your direction changes, therefore your velocity changes. Your velocity changes, you are accelerating. This will have an impact as we keep going further, because if there is a change in the velocity, there is acceleration, therefore there must be a net force acting on the car, you, whatever happens to be changing direction. but that will be for another day. Have a wonderful day. I will see you Thursday. Potentially, tomorrow, don't forget, I sent out an announcement last week. Office hours, I've got a meeting that I need to be in, but I should be hanging around my office from 10 to 11. At 11 o'clock is when I'm calling, going to be. Tomorrow. We don't have class. Yeah, tomorrow. Thursday. Oh, okay. If, what I recommend you do is just do the estimate. Because there's some instructors who want the negative number because it tells them whether you're above or below. I don't care. I did pick up the. Sorry, okay. So, start out with the force diagram. So you've got boy on sled. The sled's being pulled horizontally to the right on level ground, so it's going in one direction. Horizontally. The friction between the sled and the ground is equal in magnitude, so you've got the foot pointing that way at 42 newtons, and friction to the left would be 42 newtons back. So the total force horizontally is 0. 42 that way, 42 that way, cancel out. So, so we have boy on sled. So think about it like box on ground. So the boy's got a normal force acting up, his weight acting down. The sled has its weight acting down, normal force up from the ground, normal force down from the person. So I got 2 forces down, 1 force up.
Yeah, me too.
So the magnitude of the normal force acting on the sled from the boy, well, that would be the same magnitude as the normal force on the boy from the sled. The sled's pushing up on the boy, the boy's pushing down on the sled. And the force that, normal force on the boy from the sled is enough to keep him in balance. He's not falling or going. I feel like I've just thrown a bunch of words at you.
Yeah, I did. Yeah, that's the one you created. I don't know why.
So the force diagram, boy, sled,
Yeah,
right.
it's okay.
It's being pulled this way with some tension, I believe.
Yeah, because
And there's friction acting back that way.
There's
friction acting this way. This would be an example of other,
Yeah.
unless you want to put some mystery object over here with tension acting back that way, but it really doesn't matter. I have weight up boy, weight up sled, and I got my counterweights of parts of that. Sled. Normal force on boy, he's pushing down on the sled. Normal force on the sled, normal force on the sled. All right. Did I just throw too much at you at once?
No, it's better if I see the picture.
Okay, yeah, that, with any of the problems where I recommend trying to draw a picture of force diagram, that's a classic way to start. In the problem, I state that they're moving horizontally. So there is no vertical movement at all, no vertical acceleration. Therefore, those have to be equal in magnitude. So whatever his weight is, that's that normal force. If they were different, then either he's accelerating downwards or accelerating upwards, but he moves with the sled and the sled's moving horizontally. So I know that those, so whatever that is, what you calculated, that's gonna be the same number. That question C was, what is the normal force the sled, the boy exerts on the sled?
On the sled.
So what is the magnitude of the normal force acting on the sled from the boy? So that is this force right here. That's C, problem C. Problem D, the normal force acting on the sled from the ground. So D is asking for this. Well, that's coming from the boy. That's this number. Those two are equal because he's in equilibrium. So if you have that, you have that, you have that. For the sled, it's in equilibrium vertically. I have weight acting down. I've got that acting down, which you just calculated in part C. This is what's keeping it from going through the ground. So this has to, well, basically counter the two going down. So you know that one because that was the answer to part B, I think. Yeah. B was sled, yeah. So
This would be the answer for this.
that's the weight of the sled. That 58
Oh.
point, that's this number right here. The answer to part A is this. That's A. The answer to part B is this. The answer to part C is this. D is, the answer to part D is finding this number. And then I state what this tension is and give you that that's 42 newtons. I say that that's the same magnitude, so you know what that value is. And so the magnitude of the friction force acting on the boy from the sled, well, the boy's moving with the sled.
So it would be 42.
If the boy's moving with the sled, and the sled is in equilibrium,
0. Okay.
there is no friction acting on the boy.
Can I turn these in?
Oh, that's right. Yes.
Thank you.
Okay.
The graph, do we print it out and turn it in, or do we send it via like the Blackboard?
Yes. All right, so my ideal is that it would be printed out and included with that. Not always realistic. So if you can submit it, the graph through Blackboard and hand this in on paper, but just make sure on this you write graph on Blackboard.
Do you mind if I print it out for Thursday? Or
No,
do you-
that's fine.
Okay. Thank you.
Or maybe this will be finally the time I get everything graded the next day. Odds against it.
Sorry, something's just not clicking for some of these.
All right, so you see that there are two forces acting on the boy.